All right, so now we're going to look at an example of creating a voltaic cell from scratch. Remember that the voltaic cell is going to need a cell potential that is in fact positive. So each half has to do either a reduction or an oxidation, and together they need to add up to be a positive value. Remember that your reduction will be whichever one is on the table that is the largest positive value, and you can think of your oxidation as the one that's on the table that's the lowest negative value. And because the oxidation, you're looking at the table's number, remember we're going to flip that reaction around, thereby making the potential positive. All right, so let's look to see what we've got here. First off, we're being told that we're making a solution out of some copper and some copper sulfite. Let's go ahead and put them in beakers. Beakers are nice because they're the easiest ones to draw for a voltaic cell. Obviously, batteries are not in beakers, but they're nice to draw. And you can see in the textbook that they've got some examples of other versions of voltaic cells. All right, so this is my chunk of metal. And here's another chunk of metal. So this is just the base drawing, right? You need two pieces of metal. You need the metal to be connected through some sort of system. So let's do a light bulb. If you want to do a battery or a voltmeter, that's fine too. You need to ensure that the metals are each touching into the solution. And you need to make sure that the salt bridge is also touching in the solution. If the metals do not touch the solution, you won't get a current. And if the salt bridge is not in the solution, you again will not get a current. All right. So the copper metal we'll just put on this side. Here's our copper. It's a copper 2 sulfate, so there's our copper 2. And on the other side, it says that we're going to have an aluminum metal strip and aluminum nitrate. So aluminum plus 3. Okay. If you flip-flop your copper and your aluminum, it's not going to be a big deal, right? Because we're just looking for the flow of the electrons, and because we're looking for a flow more so than where you've placed them, I'm just going to be looking to see if the flow is going in the right direction. All right, so again, next what we want to do is we want to go to our table, and we want to find our aluminum and our copper. Remember that our copper 2, we want this one going to copper solid. So again, don't accidentally grab the one that's copper 2 to copper 1 or copper 1 to copper solid. They're all right next to each other, so be really careful about that. And we've got a 0.34. So that's a nice positive value. So 0.34 would be what the reduction looks like. All right. We're going to go back to our table, and now we're looking for aluminum, and you can see aluminum's right here with a negative 1.66. So again, looking at aluminum as the reduction, it's a negative 1.66. That immediately tells us that the copper will in fact be reduced. We're going to keep this as a reduction. The aluminum is now going to be oxidized. So we're going to get rid of the reduction possibility, and we're going to instead look at it in terms of an oxidation, which would be positive 1.66. All right, so let's write our balanced equation, which I'm going to do down here at the bottom. Again, the copper needs to be gaining electrons, so it's going to be copper plus 2, turning into copper solid. And that would be gaining 2 electrons. And since I don't have too much space, I'm actually going to merge the aluminum with it right now. We have, on this side would be the aluminum 3, right? Aluminum plus 3, excuse me. And then we would have also aluminum solid on the left. And then since aluminum is oxidizing, aluminum needs to be releasing 3 electrons while this reaction is taking place. So the copper half reaction is in orange, the aluminum half reaction is in blue, and remember you cannot leave it like that. You got to get rid of these electrons. There can never be electrons on either side of the reaction. So that means that in order to get aluminum's 3 electrons to cancel, we need to get a common number with 2. So that's going to be multiplying by a 2 to get a total of 6 electrons. So multiply the aluminum by 2 and the other aluminum by 2. And then the copper, again, we want to get that 2 to be a common number with 3. So we're going to multiply that by 3 to get a 6. Copper ions by 3, copper solid by 3. No water needs to be added. No hydrogen ions need to be added. And now we can delete off our 6 electrons. So we know the total number of electrons being passed is going to be 6 moles as this reaction takes place. We also know that since the aluminum was being oxidized, the aluminum metal is sitting in solution, acting as the anode, right? Oxidation, anode, both vowels. Our copper, on the other hand, is over on the other side, acting as our cathode since this is being reduced. That means that our copper ions are joining back into the solid form, while our aluminum metal is turning into aluminum ions. And so that aluminum metal is going to get thinner and thinner as you look at it. So this is the basic sketch. And so we want to do 2 other things, right? We want to make sure that we've selected some sort of salt bridge. And so let's say this time we want KCl. Again, anything that is going to be neutral as ions will be useful as neutral in relation to the charges. And again, notice since the aluminum ions are turning into, they're coming off of the aluminum solid and joining this cell, that means that the negative charge needs to flow out of your salt bridge. And since copper ions are disappearing onto the copper solid and this copper cathode is turning larger and larger and larger, we need to have potassium ions make up for the positive charges that we're losing there. Last thing we need is just indicating the electron flow. So since oxidation is where electrons are being lost, the electrons are going to flow out of the aluminum cathode. The electrons will then pass over to the copper cathode, where copper ions will find them and join together, making this electrode much larger, and again, making the aluminum electrode much thinner. All right, there's drawing a voltaic cell from scratch.